of channel model. Okay. So channel model, just let me see where it is. So that means channel model means in this, if you remember that our basic block say till means in that last class till now we are discussing about things here. Okay. So today I will discuss here, but I will discuss later also. But after that I will talk about little certain general prerequisites. Okay. So let us talk about channel first. And please remember, so this is a different book that I am following. Digital Communication, Proakis and Salehi, 5th edition. Please, Digital Communication, just let me write it. Digital Communication. The book is available in internet. 5th edition, please remember, 5th edition. Proakis, Salehi. Okay. So anyway. So here we will talk about channel. Let us see, and that these things we have already studied, that K-bits grouped together, these, that, KYN module, digital modulator, either it is PCM or PAM, that MRE modulation n greater than 2, all these things we have studied these things. Okay. So mainly we will talk about the communication channel, which is mainly the basic model, then we'll why the communication channel means a variety of physical media. You see that including the wireline, fiber optic cables, wireless, including microwave, and all these things, and also the acoustic media for underwater communication. Okay. And what are the problem? Problem is the additive thermal noise, man-made noise, means automobile ignition noise. This is very important nowadays for this automotive car kind of thing, and also atmospheric noise like electrical lighting, discharges, thunderstorm, and all these things. Okay. So now digital demodulator, I am not at this point. I am not discussing this. So let us go to the channel actually. So it is the first chapter. If you see communication channel and their characteristics. So let us and there are certain well-line channels. And well-line channels, so two things. One is the well-line channel. Okay. Mainly, that means the well-line channel is the guided. It is the guided electromagnetic channels, and another is some sort of a well-line channel, and another is the fiber-optic channel. Where here the data rate is much higher than the well-line channel. Okay. So now. This is some sort of the picture. We will find it, and the next is wireless electromagnetic channel. That means for our wireless mobile communication, this one. Okay. Now, so for that also the picture is given. So and general the one is the ground wave and another is the sky wave preparation, propagation. That means in this way and another one is some sort of ionosphere and communication, that is the sky wave. So I am not discussing these things because we will get these things. And at this point, don't bother about signal multipath and signal fading. We will discuss this later. Signal multipath and signal fading, we will discuss this later. And yes, this is important. At least that 4 channels. That means well line, wireless media, fiber optic, underwater and acoustic. At least these 4 channels you should read little bit actually that what it is. And there are certain storage is also called channel, but anyway, forget it. Now we'll talk about little bit of for all these channels, the commonality, the mathematical models for communication channels. Let us discuss. Okay. Now the simplest model, this is additive noise model, additive noise channel. Additive noise channel, whatever noise is there, it adds. Okay. And in this model, my transmitted signal is ST, it will be corrupted by NT, so that RT is ST plus NT. That means that whole channel, I am just saying the channel I am modeling it, this is my transmitted generated waveform. That noise, that channel is basically some sort of, you can model this one as ST will be the input, inside the channel the noise. Please see, try to understand. This whole black box is a channel. Noise is, see, NT is not coming outside, NT is already inside. That means that noise is, channel is characterized by additive noise. That I am telling. So that ST is the input and ST plus NT is the output. And these NT, first of all, that you can say, I will have ST, why not ST into NT? Why not ST into e to the power NT? But no, we are making the life simple. We are saying, it is the ST plus NT, because then that is easy to analyze. Okay. And also I am saying that this noise, it is a Gaussian. Okay. So first of all, that this is a Gaussian noise, generally zero mean with some variance. Okay. So then it is called additive Gaussian noise channel. And also on top of that, so it is additive Gaussian noise channel. Okay. Now, sometimes we add a factor whiteness, additive white Gaussian noise. Okay. Now regarding this whiteness, please read little bit of your signals systems book. That what do you mean by white noise? That means it is the white noise thing is that it is a white. If it is the white noise process, that means then actually its spectral density is flat. That means correlation metric, that is like a delta function. Please read this whiteness part. What is white noise? Just Google it, whatever it is. White noise. What is? Okay. Please read it. Or maybe I will cover later. Okay. Because on top of Gaussian, I am putting another adjective. It is also white. Okay. Anyway, so now another one, that means say instead of this simple additive noise channel, I am saying that is a linear filter channel with additive noise. That means my ST will be the input transmitted signal. My channel is some sort of a characterized by CT and NT, where your RT is basically it is the convolution. That means that ST is my input and ST convolution CT plus NT is the output. Okay. So this is my received signal. This is the input of the receiver. Try to understand. This RT is the input of the receiver. That means if your CT is delta T, then you are basically going to the previous model. Okay. Now, sometimes that we say that CT equal to just alpha into delta T. Then RT equal to alpha ST plus NT. So alpha is some sort of an attenuation factor. That means when sometimes we say that CT equal to alpha delta T. Delta is the inverse. Okay. So I have, and alpha is generally less than 1 something. Now that ST, and if I just do the basic channel output RT, that is C tau ST minus tau d tau NT, that anyway. See, please try to understand. Here I am doing convolution, but I am not talking about time variance or timing variance. Okay. So first of all, from the previous additive noise model to I am saying additive white, additive Gaussian noise. Then I told additive white Gaussian noise. Then I told the linear filter channel with additive noise. Okay. Then I am saying that linear filter, but it is a linear time. So here I have said linear filter channel. Linear filter channel. Now I am saying no, it is linear time invariant because you know time variant filter channel. Okay. So linear time variant means basically your RT is basically because CT and basically CT tau or C tau T. So the two terms, the tau is coming into picture. Tau is the amount of actual time. So it is your RT is basically this is in terms of tau. C tau is say C tau is T minus tau D tau, but C tau with some T. That means that your output is actually dependent on not only the C is not only dependent on tau, C is also dependent on tau and T. That means absolute. Okay, that at least that this linear time variant things you have studied in signals and systems. Please brush up those knowledge. That this is that here that linear time. So that means that what is the linear time variance? Basic essence is that now in for linear time invariance, what is the basic essence? Basic essence is that if this is now, if I give at this point, if I give the input and I get the output, say output is some output. Now, if I give the same input after 1 year to the same plant, that after 1 year, that I will get also same output. This is the basic idea. Okay. But linear time variance means no, it is not same. It depends on your absolute time. This is the basic essence of linear time variant. Anyway, so this is the linear time variant channel means your RT will be NT plus ST convolution C tau comma. Okay. Now that the good model, and we are talking about that multipath. Okay, if you remember, I told you that where it is. Now, somewhere I told you to stop thinking of multipath. Multipath means what? Multipath means basically, say I am doing a communication from this point to this point. Say there is a wall. Now, what will happen? One is a direct line of sight. This is called line of sight. Okay. And another one, say it will reach another one, maybe like this. Now, what I am saying that C tau T. Okay, that your channel, okay, say this is your A and this is your B, that your channel C tau T, the time variant, it is basically sum of delayed impulses. And sum of delayed, good model for multipath signal propagation through physical channels, such as say, I know they are saying mobile, I am rather saying this one is easier to understand. Mobile cellular radio channel. Okay, so it is like that I have some say A1T delta tau minus tau 1, A2T delta tau minus tau 2. Okay, tau 1, tau 2 is the say tau 1 is say this delay for say 3 path. This is line of sight path, first path. This is second path. This is third path. That means L equal to 3, multipath number of path is L equal to 3. And for individual path, what is the delay? Okay. So that means that alpha AKT is represent the possible time variant attenuation factor for L multipath. That means for this one I have A1, for this one the attenuation is A2, for third one I have the attenuation in A3. I am saying no, this attenuation is itself dependent on time, so that's why I am putting an AKT, and I have each one delay is tau k, so I am doing this. Sometimes we say that that this is a time variant version, and it is sometimes that if you substitute this one in 1.3 minus 3, 1.3 minus 3, say in this one, then what is your R? R will be that one. If you do the convolution with delta, basically the same thing will come. So your RT is AKT ST minus TK tau K MT. Okay. Or sometimes we say that it is not AK is constant. Say sometimes we say that this attenuation, it is not dependent on T. Okay, but many a times attenuation is dependent. So that means you see basic point is what? L number of multipaths. So that means 3 number of multipaths. L equal to 3. A1T ST minus tau 1. That means say for I am assuming for if I just assume that for this one delay is 0 for minimum, say tau 1, and I can take that tau 2 is with respect to this, tau 3 is with respect to, or we can say now it is absolute delay. So tau 1, tau 2, tau 3. And see, this the simplest one is, say I am removing this T business. It is dependent on only the path. Let's say path length, because you understand that if path length is more, so that attenuation is more because due to some physical medium. Also, sometimes we say it is dependent on time because say I am doing a long distance communication and say there may be a rain somewhere. Okay, in some path after some time he is facing some problem. So rain absorbs the energy. So raindrop. So I have some sort of a amplitude dip kind of. This attenuation is more. So that's why that it is prudent to use this time variant path. Okay, because anyway, these are basically, so that means for multipaths. This is especially in a mobile communication, means this is my multipath is quite common. Okay, and for a normal communication, say for modeling, we say okay, this is this linear LTI kind of thing, C tau ST minus tau. This is also this one, and this one we use often. Okay, now let us go to say chapter 1. Okay, so first of all, please remember this book is a bit advanced. Okay, so it's not like Barnard's Law. Okay, Barnard's Law is generally a bit easy going book. So this book is little advanced. So read carefully with time. Okay. So here we will talk about, and most of the things we will see that you know, but we'll try to appreciate it. See that we have certain definitions. So these definitions already you know in a generic form, but for communication systems we use it. First of all, that sync function that you know, sync of T is some sort of a signal like this, and it goes minus infinity plus infinity. At T equal to 0, it is 1. Okay, this is 1 T. Okay, this symbol. This is some sort of a box function. Okay. Okay, so box function, that's why they have put some sort of a big pi. It is like that. That means box function is something like this. Okay, it is that 1, then it is it is 0.5. definition is this is 0.5, this is minus 0.5, this is 1. But we say at this point I am defining the function in this way that this is also half. Okay. Now this is called box function, sometimes we say pulse function. This is the signum function that we know. Signum function is like this. Okay, but at t equal to 0 it is 0. Okay, this is plus. There are many different ways of this one is half. And there's this triangular function or delta function where basically you are doing the convolution of this one. If you do the convolution with its own, what will happen? It will be like this. Okay, so when t0 to 1, it is minus t plus 1. Okay. At t equal to 1 it is 0, t equal to minus 1. From between this range it is t plus 1. Basically this block is this one, this block is okay. If I do the convolution of this function with this, basically you will get that the output at t equal to 0, this is 1. Okay. And the unit step you generally we say about ut, but here they have defined with u minus 1t. It's okay. So, but unit step also you know it is like this, but here it is defined as 0 point. Okay, this one you know these things. Okay, now and you know this one, that means by say signal and Fourier transform. Okay, say means see that please try to understand. I am telling you these property a little bit: duality, conjugacy, time shift, modulation, convolution. Already you have studied a lot. Parseval's theorem, Rayleigh theorem. That Rayleigh's theorem is basically a special case of Parseval's theorem. Means when yt equal to xt and xt extra t is the mod of xt square, then basically x star f, that is mod x. Then this one will come to this when y equal to x. Anyway, so this one, so this and then so these 4-5 theorems, especially duality, check that xt and minus x. What do you mean by that? Anyway, so now that we will talk about bandpass and low-pass signal representation. Because why suddenly I have jumped to this, you will find it, means I will take a little bit of, I will again go to the baseband modulation, then it will be clear to you that why it is required. Now, first of all, that bandpass signal is basically in many cases, information signal is a low frequency signal. Low frequency is some sort of a baseband, we say. Okay. For audio application, low frequency signal is called bus. Okay. So here, low frequency signal is generally we talked about that baseband signal. But in almost all cases, the spectral characteristic of information sequence do not directly match the spectral sequence of the. This is very important. Okay, so that's why I have taken this one. That suddenly, why will I do? See, the process of, please try to, these lines are deadly. The process of communication consists of transmission of an output of an information source over a communication channel. Instead of transmission of information source. Okay. And in almost all cases, the spectral characteristics of the information source or information sequence do not directly match the spectral characteristics of the communication channel. Okay. That means that source has some sort of a information in a frequency range of say 0 to 100 Hz. Okay. Say you like to transfer ECG signal, or forget about ECG signal, you like to transfer some, say you are somebody is beating the drum. Okay. So that frequency is something say you are listening, that means maybe at or rather somebody is talking, forget it. Somebody is over telephone, somebody. Say somebody is talking. Okay. So speech is generally, you see, though you know that 20 Hz to 20 kilohertz, then human ear can listen and all these things. But speech, if you see the human speech, the characteristics, the spectrum or frequency response, you will see that signals frequency response, if you plot, say this is your SQ, some speech. Now if you plot mod of this F versus F, you find that it is something at, say, this is 3 kilohertz. So this type of characteristics. Okay, with 20 it is there, but that energy is very small. Okay. So that means it is some sort of a 3 to, some sort of, I can say 3 to 50, and say 1 to 15 in that range, mostly the energy is there. Now, say you like to transmit this information through the channel. But your channel, it may so happen that your channel can transmit, channel has also some characteristics. Channel can transmit in some sort of a 2.4 gigahertz, that frequency range. Okay. So you have to somehow frequency translate this signal to that range, otherwise you cannot transmit. Okay, because channel has a frequency response. But the channel's frequency response, so this is your SA. And channel, you just plot CF, mod of CF versus A. So it has something in that range, which is something, say 2.2 gigahertz, 2.4 gigahertz, something like that. So you have to do something so that this information signal should be translated to this zone and then it can be transmitted. So that they are saying that information do not directly match the spectral characteristics of the communication channel. Means information signal cannot be directly transmitted over the channel. In many cases, the information signal is a low frequency, that baseband signal, 3 kilohertz. In many cases, an available spectrum of the communication is higher frequency, like 2.2 gigahertz or 2.4 gigahertz. Therefore, at the transmitter, the information signal is translated to higher frequency signal that matches the property of the communication channel. This is the modulation process in which baseband information signal is turned to the bandpass modulation signal. Okay. So the main properties in this section, we will study the main properties of baseband, that is low frequency, and bandpass, which is relatively high frequency signal. Okay. Now, baseband is low frequency, bandpass is high frequency. This is the basic part. Now, this Fourier pair that we have studied. Now, that if you so these Fourier pairs you study a little bit, that you have already studied most probably many a times. Okay, and the here that there are certain the Fourier transform of a real signal xt has Hermitian symmetry. That most probably you have studied. X minus f equal to x star f if it is a real signal. From which we can conclude that if you take the mod of this one, they are saying that is mod of x minus f equal to mod of x. And angle of, if you take the angle of x star f, that is minus of angle of x f. Now, please try to appreciate this one. I'm just reading this one. Please try to appreciate. Because I'm just teaching signals little bit in a different way. Now, for real signal, the magnitude of xf, that is mod xf, that is even. That is the even function of x. That is the even function of x. And the phase spectrum is a odd function. Okay, phase is odd. So now, do you appreciate that why it is coming like this? Can you appreciate this one? That suddenly y phase of x conjugate f, it is coming minus of xf, minus of this. Okay. Now that if this is
Sir, how did that angle part come?
Because if xf is a plus jb, x star is a minus jb. So angle will be negative. So that means angle of x star is angle of x. Is it okay?
No, sir.
Is it okay?
Yes, sir.
Yes, sir. Yes, sir.
Basically, he is trying to do that. Okay. Now, so but that is and so I can write x star f is x minus f minus of. And please try to understand all this small f I am writing capital F. Please, I have a agenda. When it is hertz, kilohertz, everything, I write capital F. When it is digital frequency, I write small f. Okay. So forget about digital frequency. So if as it is continuous signal and everything, I am writing capital F. So I generally follow this notation. I don't, though in the book it is written small f in your all say signals in first class, but generally I follow capital F. You will understand this. Means if you follow this, okay. Generally, if I teach signal systems, I write capital F. All Fourier transform analysis for continuous time systems. Okay, because there is certain advantage when you study DSP.
Sir, what is the meaning of complex Fourier transform, like complex number Fourier transform?
Complex number Fourier transform will give you the complex. Generally, if you take a signal and do the Fourier transform, generally it will give the complex.
So, but in the graph, we just draw frequency versus the magnitude of Fourier transform.
So that's why you check what I have written over there. Because sometimes see, always I write what? Mod. You plot mod. Because if you do that ST, if you do the Fourier transform, you get SF. Okay? For any signal, if you take ST and if you do the SF, you will, most of the time you will get the complex. Is it not? Or always you get real? So complex, how will you plot? Either you have to plot the magnitude mod SF by F, and see, ideally when you plot, you plot in this way. You should this is mod of SF, this is angle of SF. If mod of SF versus SF is the magnitude spectra, this is called phase spectra. Magnitude spectra, phase spectra. Okay. Now, here we have seen that for now the Fourier transform of a real signal has Hermitian symmetry, that is x star f equal to x minus f. Now, if I plot the and if I take the mod of this one, that is x of f mod of x minus f, that is equal to mod of x star f, that means mod of x f, that means it is, if your spectrum will be, this is even function of f. And if I take the angle of x minus f, that is minus of x f, so your odd phase spectrum, that is odd function. That means, see, that this is xf versus f means, so this is your, say something mod of xf. So please take this is as a, and say this is this dotted line, I am not very sure what that is. So most probably this is odd function. So this is some sort of a, say they are taking the angle of. But generally this type of leading phase people generally don't do. Anyway, so generally people plot like this. Anyway, so they have taken a very hypothetical case. Anyway, so now that, so that means this is a odd function and this is an even function. This is for real signals. Okay. Now, first of all, that because of this symmetry, that means the all information about the signal is in the positive or negative frequency. That means if, because you see because you are transmitting the signal, that is basically a real signal. Okay. Now, for real signal, spectrum is like this. If you just take any real signal and do the Fourier transform in some standard package, you will see your magnitude response will be even and phase response will be odd. If it is even and odd, that means if you have only this part of the spectrum, okay, that means you have this and you have this. You will have the other part because you know that this is even and that is odd. Okay. So that a real signal xt, and also we define the bandwidth W is basically means where the frequency ends actually. Okay. So that means that this, that if we know these things, that is sufficient. Okay. And that a low pass or baseband signal, that is that spectrum which is located with zero frequency. That is speech, music, video signals are all low pass signals. Okay, they have different spectral characteristics and bandwidth, but they are basically a low pass filter. And usually low pass signals have low frequency signals, which means that in the time domain they are slowly varying signals. Okay. So this you know with no jumps, no sudden variations, and what is my another thing is that we talked about frequency support. Frequency support means generally we see this is the bandwidth, the W, and many times we say this minus f to plus f. Frequency support is something like this. This is just terminology, nothing else. This is called frequency support. That is where your spectrum is non-zero. Anyway, now now what about the positive spectrum and negative spectrum? Positive spectrum is basically we are defining in this way. That is positive spectrum, just like the positive part we are defining. When frequency is positive, I am taking the same thing. When it is negative, I am taking half of x0 and that negative. Similarly, if I take the negative spectra and I am for negative one, I am taking xf, but this is half of x0 and 0, and if we add these two, I will get the original spectrum. So that means your x plus f basically equal to xf into uf. X of f into they have said u minus 1 for u of whatever you want to do. Anyway. uf. Okay. Now for a real signal, since xf is Hermitian, so x of minus f is x plus star minus f. Please try to do it by hand. Okay. Now, so basic point is that the spectrum of a real valued bandpass. So real valued baseband. So you see that
Sir,
let me finish it then. This is the real valued basic point is that. So forget about these properties for the time being. Forget about these properties. These are basic mathematical jugglery that we will understand. So there's nothing. But basic point is that this is the spectrum of a baseband. Real valued baseband signal. The point is real valued baseband signal. That means where the spectrum is near 0, W is some finite, say 5 kilohertz, 10 kilohertz, 1 megahertz, all this. Another is the spectrum of a bandpass signal. Okay. Spectrum of a bandpass signal. That means where your basically spectrum is, see this is x of say f. I don't see it is something like that. Say this is some sort of a 2.4 gigahertz, and this is minus 2.4 gigahertz. And your spectrum is the magnitude spectrum, and say this is the phase spectrum. So this is like, and it is also inverted. Don't see that this one is that side, that one is that. So your spectrum is like this is a real valued bandpass. Okay, so that means where the spectrum is not near origin. Okay, now tell me. Hello. Please tell me.
sir, what is the physical significance of negative frequency?
See, the negative frequency is generally a mathematical concept. Okay. Now, because when we do things, basically, if the Laplace transform, Fourier transform, if you represent, it will come as a negative frequency. But if you see from a physical perspective, see negative frequency is something like that. The machine is rotating in one direction with some frequency. Okay, say some cycles per second or some RPM or RPS. If it is rotating in opposite direction, you can see in a very vague way in this way. But generally, it is purely a mathematical concept. But if you consider only positive part, you will see certain problems are there. Handling things will not be easy. Because now, why the negative frequency is coming into picture? You try to understand. See, I have a signal. What I am doing in a Fourier series or Fourier transform, I am trying to project the signal into the orthogonal basis functions. That means e to the power j omega t, all this what is like, that integral of xt to the power minus j omega t. Now, what is e to the power minus j omega t? Basically, a cos omega t plus j sin omega t. Now, if you, so that means you are projecting your signal to the complex space. Okay, so suddenly your frequency response will be some sort of a complex. Now, if you say no, I will not project my signal in complex space. That means I will do x. See, there are some transforms where your capital X not F, some value X of say G, something like that. So where you are doing integral of xt into the instead of e to the power minus j omega t, you put a cos omega t. Okay. So that means you are projecting it to a some sort of a real value function. Instead of e to the power j omega t minus j omega t business, you are project. So are you getting my things, or shall I go much deeper? Then actually. That means I am projecting it to who is projecting to whom. Do you understand the basic idea of see? Do you understand? Say I have a signal xt, and I like to understand the similarity between xt and yt, between say 0 to t. Then we generally write it. This is the metric. A similarity is. Do you know these things?
No, sir.
You know. Forget it. Okay. Dot product, do you understand of vector?
Yes, sir.
Say a vector A and a vector B. The dot product, what? How do you do? A dot B. A dot B means summation AK BK. Okay. Hello.
Yes, sir. Yes, sir.
Summation AKB. If it is a complex vector, what do you do? Summation AK B star K.
Yes, sir.
Now, if you say instead of vector is some sort of a discrete things. If I make it in a continuous domain, what I will do for a real valued vector instead of summation AKBK, I am doing 0 to t xt yt. If it is, so this is now dot product means similarity. Do you understand that? In a vector, dot product means similarity. Do you understand that? Or shall I explain?
Yes, sir. I got the correlation.
So now that means if it is a complex function, then we see similarity means like this. Now if I say yt is my yt equal to e to the power j omega t, then basically forget about this limit, this limit. I am just taking a one period kind of thing. But basically you are getting xt to the power minus j omega t. So that means you are basically calculating the similarity of xt and e to the power j omega t. Okay. And you are changing different omega, and you are, because this one you are putting a omega over here, and you are changing the omega, and you are seeing the similarity of xt with different complex exponential. Okay. Suddenly, if you project your signal in a complex vector space, so this one will be complex. Okay. So, and complex means first of all real part, imaginary part, and so this is the complex means frequency representation. And if you plot it, and if it will come, mainly it is a mathematical connotation. And that's why I am telling that means if you see purely from a vector space point of view, it will be basically output coming from the mathematical treatment. Okay. Now that rotation of some motor or small motor or something that in opposite direction. This is some sort of a mere physical interpretation. Okay. Now rather here a band. So let us again come back to our original. Now that is a bandpass signal. It is a signal whose frequency content is located around some frequency capital F0, which is far from G. Okay. And the bandwidth, the interval is F0 minus W by 2 to F0 plus W by 2, where W by 2 is this. Then in practice, now you see this is quite important. Okay. You try to understand this one. And usually we say that means I have a bandpass signal It's something like this. This is F0 and minus F0, and this is some sort of a W. Okay, so that means F0 minus W by 2 to F0 plus W by 2, or minus F0 minus W by 2 to minus F0 plus W by 2. Okay. And generally this W is much less than F0. Okay, so that means this W, this range, this W is, this is F0, this W is much less than F0. Now this F0 is called central frequency and W is called bandwidth. So now it's just like that. F0 is some sort of a 2.4 gigahertz and W is maybe your speech frequency is something, how much? 20 gigahertz. 0 to 20 means 20 hertz to 20 kilohertz is almost 0 to 20 kilohertz. So say bandwidth is 20 kilohertz. So that means 20 kilohertz is a W and your F0 is 2.4 gigahertz, something like that. Okay. Now, since the same, now if you see the one, that means the, let us again explain things. That I know that it is a real signal. I know that your the magnitude response is an even function. So I have got a even spectrum, that is magnitude response means that the mod function. And this is the mod function, magnitude response of xf. And the positive part is the x plus f and this is x minus f. X plus f equal, that means this one is same as this one. Okay. Because this is the even function. And what about phase? Phase is that phase spectra, that is phase spectra is odd, but please, can you say what about this one? That phase spectra, is it odd? Odd means it should pass through origin and all these things. How can you say? Because for baseband I understand. For baseband, say this is odd. But for bandpass, how does it become odd? Just read little bit. Okay. See that it's shown in figure 2.1 minus 2 is phase spectrum is dashed line is odd. That is, and due to symmetry of the spectrum, x plus f. That means the basic point they are saying, that means that the knowledge of x plus f is sufficient to reconstruct x8. That means what they are basically saying, see, you are transmitting this whole information, xt. Okay. Now, xt means basically everything, this side and that side, or here it is this side and this side. But what basically point is, as it is real signal, if I transmit only one half, okay, you did not transmit this part. Okay, so that means if I send half of the information, my tasks are accomplished. This is the basic point actually. So this is the last line, that knowledge of x plus f is sufficient to reconstruct x. Okay. Anyway, so we'll study these things a bit in the next class also, and I will also explain that how this baseband is coming into here. Please try to download this book and read this particular chapter. Then it will be easy for me and easy for you to understand that. Because what I am telling in a bit means I am not deriving this thing, because already this is all signal sequence. So please, if possible, please download and read. If you just start with Proakis Salehi, then it will come like this. Thank you very much. We'll discuss again on